Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is a continuation of my series on the Math Lovers book. I have 3 volumes. This is a 3 volume series of math textbooks I wrote about 3 years ago, and it's available on Amazon.com if you're interested. Each of these books is available both in paperback or in Kindle. I think they're $30 each paperback, $9 each Kindle. I think they're a good buy. And like I said, there are 3 textbooks on mathematics. I talk about them in my other videos in this series, so I won't say any more. But you can check them out. And in case you don't want to spend the money, you can watch my videos, which are free. I'm doing a series of free lessons on the Math Lovers book, and I'm up to chapter 2 of volume 1. I think I'm most of the way done with this chapter. I began a sub-series on what are called aliquot sequences. This is section 2.5. These are sequences where each number in the sequence is the sum of the non-trivial divisors of the previous one. And a special case of that is perfect numbers. That's what I'm going to talk about today. So anyway, let's begin. So what are perfect numbers? Well, a perfect number is just a number that's equal to the sum of its what's called aliquot divisors. In other words, all of its divisors except the number itself. And perfect numbers are very rare. They were discovered by the ancient Greeks, I believe. 6 is the smallest perfect number. Pretty easy to see. The aliquot divisors of 6 are 1, 2, and 3, and 1 plus 2 plus 3 equals 6. Pretty easy. You might think they're pretty common, but they're actually not. The next one is 28. And you can check yourself. Aliquot divisors of 28 are 1, 2, 4, 7, and 14. Those add up to 28. And then they get big pretty fast after that. The next one's 496. Next one after that is 8,128. Probably should have made a table of these, but and then yeah, after that, that's the fourth one. I think for a while there were some medieval mathematicians that thought, the first one has 1 digit, the second one has 2 digits, third one has 3 digits, fourth one has 4 digits. A lot of people thought the fifth one was going to have 5 digits, and that pattern was going to keep continuing, but it doesn't. The fifth one actually has, I think, 8 digits. I don't even remember the number offhand, but it's a very big number. They get very big very fast. But they have a pattern to them, and I'm just going to switch to the next slide. And also, all the perfect numbers that are known are even, by the way. And I think it was Euclid, if I'm not mistaken. Yeah, it was Euclid, the 3rd century BC Greek mathematician, very very famous Greek mathematician. I mentioned him a few times already. One of the things he discovered was he discovered a formula for every even perfect number. He said, I mean, he didn't discover a formula for every even. What he discovered was a certain type of number has to be perfect. He said if p, let's p be a prime, little p, small prime, we can consider the number 2 to the p minus 1. If that is also prime, that's what's called a Mersenne prime. Sometimes people write m sub p, 2 to the p minus 1. If m sub p is a prime number, which it usually isn't for Mersenne numbers, a Mersenne number is just a number of the form 2 to the p minus 1, a power of 2 minus 1. P doesn't even have to be prime for that. But it turns out that in order for m sub p to be prime itself, the p has to be prime. That's a necessary but not sufficient condition. I talked about Mersenne primes already a few lessons ago. Mersenne primes are very rare. I think there's only 52 that are known. And for most of history, the largest known primes have been Mersenne primes. The largest known prime today is also a Mersenne prime. I don't remember the exponent offhand. It's around 130 million, I think. So it's 2 to this p is about 130 million for the largest known prime, which is a Mersenne prime. I'll just call it 2 to the p minus 1, where p is about 130 million. That's a prime number. And the m sub p for this prime, which is the largest known prime, is about that has about 40 million digits. It's a huge number. I mean, if you wrote it down with standard size text, it would take about 40 standard size books to write down this number. It's such a big number. Um, but yeah, then what Euclid discovered was if m sub p is any Mersenne prime, doesn't matter which Mersenne prime. There's only 52 that are known. Then it turns out that if you take 2 to the power of p minus 1, so you take the power p, you subtract 1 from it, and you raise 2 to that power. That's a power of 2. It's roughly half the size of m sub p. It's actually half of mp plus 1. So you multiply those two factors together, 2 to the exponent p minus 1 times m sub p. It turns out this number has to be a perfect number. Euclid proved it. It's not that hard to prove, actually. I'm not going to prove it here, but Euclid proved this in the 3rd century BC, and you can check for yourself. If I think the smallest known Mersenne prime is 2 squared minus 1, which is 3, so m sub 2, if you like, is equal to 3. And then you take 2 to the power 3 minus 1, or 2 squared. That's, am I doing this right? Uh, no, the exponent was 2, I'm sorry. So you take 2 squared minus 1, your p is 2. And then that 2 squared minus 1 is 3, and then you multiply that by 2 to the first power. You take the exponent 2, subtract 1 from it. So you get 2 times 3, and that's equal to 6. And like I said, 6 is a perfect number. Let's take the next Mersenne prime, 2 cubed minus 1. That's equal to 7. And then we multiply that by 2 squared, because we're just taking the exponent p equals 3 and subtracting 1 from it. So you multiply 2 squared is 4, so you multiply 4 times 7, that gives you 28. And it turns out, I think the next ones are next values of p that give you a Mersenne prime are 5 and 7. They're just the next two primes. And you can check for yourself that those give you rise to the perfect numbers 496 and 8128. So whenever you have a list of Mersenne primes, you automatically have a list of perfect numbers. You might have more, but what Euclid didn't prove was that it turns out that every even perfect number has this form. He proved that it was a necessary condition, but not a sufficient condition to get even perfect numbers. We still don't know about odd perfect numbers, by the way. I'll get to that in a minute. But it was Euler, another very famous mathematician, much later from the 18th century, Leonhard Euler. A lot of people think he was the greatest mathematician of all time. Certainly one of the greatest. It's sort of a toss-up between Euler and Gauss. I think most people consider one of those two mathematicians to be the greatest mathematician of all time. Um, I don't know who was greater. They're kind of hard to compare. But anyway, Euler discovered that this was also a sufficient condition. In other words, any even perfect number has this form. It's equal to m sub p to the p minus 1 for some prime p, such that m sub p is prime. And then you multiply that by 2 to the power p minus 1. That automatically, or no, he said that every perfect number has this form. There is a value p that makes that true. And his proof was very complicated. I've actually seen his proof. It involves very complicated math. It involves algebraic number theory. I actually think I know how to prove what Euler did, that this is a sufficient condition. But it's a very complicated proof, and I'm not going to go over it here. It's way beyond the scope of my series. For those of you who are curious, you can look it up. But so that's what's called the Euclid-Euler theorem, that a necessary and sufficient condition for a number to be perfect is that it's equal to a Mersenne prime m sub p times 2 to the power p minus 1. Pretty powerful result. And since we only know 52 Mersenne primes, that means we only know 52 perfect numbers. We still don't know any odd perfect numbers. And by the way, the Euclid-Euler theorem doesn't say anything about odd perfect numbers. Now I'm just going to talk about odd perfect numbers. Odd perfect numbers, if they do exist, nobody's discovered any odd perfect numbers. But we do know some things about them if they exist. It seems very unlikely that they exist. And these are just 3 conditions they have to satisfy. For one thing, I said, and this is outdated, by the way. I wrote my book about 3 years ago. I think I wrote this section even longer ago than that. I think at the time it was known that the if an odd perfect number exists, it has to have at least 1,500 digits. I watched a YouTube video pretty recently, and now I think the it's 2,200 digits. I think now we know that an odd perfect numbers have to have at least 2,200 digits, which is pretty big. I mean, a 2,200 digit number would be like about, it would take about 5 pages to write it down. So these are some pretty big numbers, you know. So not only that, but it would have to have at least 9 distinct prime divisors. I think it might be 10 actually. And I actually know the guy who proved that you need at least 9. Before he proved this result, I think it was the limit was 8. But it was a friend of mine named Neville Robbins. I have no idea what's happened to him. I haven't talked to this guy in over 5 years. He used to be a good friend of mine. We used to go to a lot of math conferences together. Kind of a strange guy. I don't want to gossip about him, but I met him when I was at UC Berkeley. Very smart man. And he's published over 100 papers. Very, very successful mathematician. I've only published 4 myself. So he's light years ahead of me in terms of the amount of math he's done. I don't want to say any more about him because I don't want to get in trouble. But then so that's the second condition. Third condition is this is actually easy one to prove, and this was actually proven I think in the 17th century. It has to be the product of a prime and a square. And that already that's a pretty strict condition. In other words, if you look at this prime factorization, remember it has to have at least 9 distinct prime divisors. Well, all but one of them is has an even exponent. Exactly one of the prime divisors is multiply. It has an odd exponent, and every other one has an even exponent. So they're pretty rare. And there's more conditions besides just these 3. I happen to know these 3. And I'm pretty convinced that there are no odd perfect numbers. I'd be extremely surprised if anybody discovers an odd perfect number. As a matter of fact, I was so confident that there were no odd perfect numbers. I remember I went to a math conference about 20 years ago. I was eating lunch with some fellow mathematicians, and I told one of the guys, we were all number theorists at this table, and I told one of the mathematicians at this table, I said, I'm virtually certain that there's no odd perfect numbers. I mean, I said I think that's about as certain as the truth of Goldbach's conjecture. I don't know if I said that to him, but I think just about every mathematician in the world believes that Goldbach's conjecture is true, namely that every prime greater than 2 can be written as a sum of every even number greater than 2 can be written as a sum of 2 primes. Everybody believes that's true, even though nobody's proven it. And I said I have the same certainty. I don't know if I mentioned Goldbach's conjecture, but I basically said I have the same certainty that there's no odd perfect numbers as that. And it was kind of funny because this guy disagreed with me. He said I think there are odd perfect numbers. His inclination was the opposite of mine, but I think it would be very weird. I mean, if there are odd perfect numbers, why should the smallest have at least 2,200 digits? I mean, I think there is some kind of principle in math, maybe in science. I don't know. If something, if something, things in math are only true if there's a good reason for them to be true. That's not a theorem, but that's kind of a principle of math. If some mathematical statement is true, there's usually a pretty good reason for it. Things don't just kind of happen. Weird things in math aren't just true by accident. And I think if there was an odd perfect number with over 2,200 digits, I think it would be pretty damn weird. I don't know why that would be true. I don't think there's any good reason that there should be an odd perfect number with that many digits. So I mean, I could probably bet $1,000 that I mean, I don't know if anybody during my lifetime is ever going to either find an odd perfect number or prove that none exist. But I would bet almost my entire life savings on there being no odd perfect numbers. I'm just very convinced that there aren't any. But maybe some of you guys disagree with me. I don't know. You know, it's fun to make conjectures like this, but my inclination is to think that there are no odd perfect numbers, and I'm pretty confident this is true. Anyway, that completes my video for today on perfect numbers. Thank you for watching. Long live math, and I'll see you guys next time. Bye.